Okay, we are live.
Okay. Hey, welcome to all joining us today for the third presentation of the 2021 New Vistas in Astronomy lecture series hosted by the Fred Lawrence Whipple Observatory. And the Whipple Observatory is the largest field installation of the Smithsonian Astrophysical Observatory outside of Cambridge, Massachusetts. And we're located about 35 miles south of Tucson. This is the 51st year of the SAO sponsorship of the lecture series, which has been a source of information for the local residents to learn about the science taking place in their backyard. So today we are honored to have with us Dr. Kimberly Arcand from the Smithsonian Astrophysical Observatory. Dr. Arcand is a leading expert in astronomy visualization and has been a pioneer in 3D imaging, printing, and extended reality applications with astrophysics data. Dr. Arcand studied molecular biology at University of Rhode Island in 2013. She earned a master's degree in public humanities from Brown University, focusing on image and meaning research. In 2020, she completed her doctorate at the University of Ortega. Dr. Arcand initially worked in a public health, importantly studying Lyme disease. In 1998, she joined, while working as an instructor at the University of Rhode Island Computer Science Department, she joined the Smithsonian Astrophysical Observatory and NASA Chandra X-ray Observatory. And having a childhood desire to be an astronaut, this appointment allowed her to get a little closer to that dream. 2010, Kim received the International Year of Astronomy Manny Baumick Prize for Excellence in Astronomy Education and Public Outreach. 2016, the White House selected her as a change maker at the United States of Women Summit. She also received the Smithsonian Institution Achievement Award in 2016. Dr. Arcand is principal investigator of the Aesthetics and Astronomy Image Response Research Project at the Harvard Smithsonian Center for Astrophysics with international participation. Kim is an expert in studying the perception and comprehension of high energy data visualization across the novice expert spectrum. Her current research involves sonification of spatial data, screen-based holograms, and other intersections of emerging technology and astrophysics. She has co-written 7 nonfiction science books, including her first 2 science-related children's books that were published last year, titled An Alien Helped Me Through My Homework, co-written with Lisa Smith, and Goodnight Exomoon. We are honored to have Dr. Arcand join us today to speak with us about her latest work. So Dr. Arcand, take control.
Thank you so much. That was a really lovely introduction. I'm just going to share my desktop and start the slides. So we're going to talk a little bit today about some of the work I get to do working with sound and virtual reality and 3D modeling. Hopefully you'll all enjoy it. I am, as mentioned, have a circuitous background, I suppose. I started out in biology, specifically molecular biology, before realizing that I didn't want to stare through a microscope for my entire career. I don't know why, but I moved into computer science as a way to essentially use data of the universe to tell stories. And then I really just happened to be at the right place at the right time. To get a job working for NASA's Chandra Observatory at the Center for Astrophysics, Harvard and Smithsonian back in 1998 before the mission launched, and have been busily working ever since in data visualization and image and meaning research. So the Chandra Observatory celebrated 20 years in space with successful operations just about a year ago. And it goes about a third of the way to the moon. So it's looking at the high energy universe. And it is just a technological and engineering marvel. Still 20 years later, this is a real cutting edge piece of equipment to be able to study the high energy universe. It's also about the size of a school bus and was the largest shuttle payload bay to ever be launched, which was kind of interesting, but also a little bit dangerous for the astronauts. So the types of things that Chandra gets to look at are really interesting things like exploding stars and areas around black holes, things like colliding galaxies, and so very much more. The high energy universe is just a really fascinating thing to be able to get a glimpse at. So Chandra, as I mentioned, is just an incredible piece of equipment, and it's part of a suite of other observatories as well called NASA's Great Observatories, which includes Hubble and Spitzer and the Compton Gamma Ray Observatory as well. And together, what that means is, along with all the other telescopes and observatories that are around the world, there's just a fantastic set of data to be able to look into and to be able to work with. So there we go. The multi-wavelength universe is just a really important thing in astronomy, being able to collect data for many different kinds of light. Versus just optical light is very, very useful to be able to help answer specific questions. So Chandra, of course, is on the higher energy scale with X-rays, but there's many different kinds of light, from the radio waves and the infrared to, of course, the optical that we're more used to, and gamma rays as well, and others in between. So it's like all of these different lights just offer a different kind of toolkit for astronomers to be able to work with. I'm going to step you through a few of my favorite images from Chandra. Many of these images are, as I mentioned, multi-wavelength, because being able to use many different kinds of light is often beneficial not only to the science, but also to the visualization. The image on your screen now is actually the official first light image of the Chandra X-ray Observatory. It is a supernova remnant, Cassiopeia A. It is just an exquisitely detailed view of a star that has exploded. And I'm going to be talking about this one more throughout the talk today. So I'll try to get into more details, but I wanted to preface this talk by just sort of bringing you through a quick tour of some of my favorite sites to see. So we are going to just very quickly glance at some stellar nurseries, for example, like the Pillars of Creation or the Eagle Nebula, star clusters and young stars like NGC 602 and the Orion Nebula, the Rosette, Westerland 2, for all these beautiful clusters of superheated gas around these young stars and star systems. NGC 6357, this is a more mature star system, a globular cluster. Now we're looking at even more mature stars such as Eta Carina that could perhaps one day explode. We're looking at planetary nebulas like NGC 7662 and the Cat's Eye, NGC 2392. Now we're getting into even more massive stars that have exploded, for example, SN 1006 and W49b, N132D and EO 102. And you can see that astronomers have a real knack for naming some of these in a super interesting way. G299, and another personal favorite is the Crab Nebula, which I'll be talking about again a bit later as well. So there are things not only just from exploded stars, but also the dense leftover cores and pulsars, B1509. There's areas around black holes like Sagittarius A star. That's a supermassive black hole at the very central region of our own galaxy. And this is a slightly farther out view of that galactic center as well. And I'll also be giving you a different representation of this later in the talk. Then we can also step out even farther to more distant galaxies, for example, and clusters of galaxies as well. So Chandra has looked at galaxies of all kinds of shapes and sizes, M106 and the Pinwheel Galaxy, galaxies that look like exclamation marks, VV340, the Cartwheel Galaxy, ARP147, which kind of looks like a ring, the Antennae Galaxies, the Whirlpool Galaxy, NGC 6240, where two supermassive black holes are in the very center region. You can see them in the bright white knots where they are in the process of merging. And of course, it wouldn't be complete without some really beautiful jets. Hercules A is just an absolutely gorgeous example of these incredibly massive jets, and clusters of galaxies that are at such enormous scales like Able 3411 through 412, Max J, and the Bullet Cluster, even a toothbrush galaxy, and one that looks like it's smiling back at us, nicknamed the Cheshire Cat, thanks to gravitational lensing. So those are just a few of some of my most favorite images and data sets that I've gotten to work on with Chandra data and other multi-wavelength data as well. But Chandra's been a really busy mission, well over 2.5 billion kilometers traveled, over 2,700 trips around Earth, over 23 trillion bytes of data collected, and over 3.6 million lines of code that have been written to operate it and collect and analyze data. Again, since Chandra goes a third of the way to the moon, it can't ever be visited by astronauts, for example, to service it and to fix it. So anything that needs to be updated and adjusted is just done through lines of code, thanks to the very talented engineers and operations teams here on the ground. So essentially, I like to think of my job as getting to play in a sandbox of really incredible data. All of those ones and zeros, they are all just a starting point to be able to make some meaning out of the science and create a visualization. So just a very quick look at how we collect that data. There's an object, for example, supernova remnant Cassiopeia A. It's about 11,000 light years away, where a light year is a distance that light travels in a year, or about 10 trillion kilometers. Chandra would be directed at that object, and it's going to be essentially recording all of the photons, those packets of energy that have been traveling from that object. And then it records it and packages it up in the form of ones and zeros and sends it down through NASA's Deep Space Network before eventually it makes its way to someone's laptop to analyze. It could first start out looking like a table. However, that information needs to be translated into a different form to be able to create the visual representation. But this table that we're looking at here is just capturing the time, the location of the observations and the X and the Y and the energy of each individual photon, each little packet of energy that struck the detector during the observation. And then we use software to be able to take that information and translate it into the representation of the object. For example, a visual representation, which would start out in, say, black and white, and which would require processing and analysis to make sure everything in it is good, no artifacts, and no smoothing needed. And then eventually we would add color and work on scaling and other processing to make the final representation. So now we're looking at a slightly zoomed in version of this supernova remnant, Cassiopeia A, our good friend. And in this case, most of the data that you're looking at is high energy astrophysics data, but we also have included an optical star field from the Hubble Space Telescope in gold to help sort of situate that this is indeed a cosmic object. But when you have a mission like Chandra that can look at things over time, because it's been in operation for well over 20 years now, that means your sandbox of data gets to be even more rich. So you can start looking at these objects over time. And time-lapse data is an incredibly important area in astronomy for research. And it's also really helpful in astronomy communications as well, because it is a way to help show how dynamic our universe is, that these are objects that are always changing. Everything is always changing. We're always changing, and the universe is no different. And so being able to track these changes over time can help the scientists learn, of course, about the expansion of this remnant as it's sweeping out into space between stars and well beyond, and then also tell you about the object itself. So this time lapse is just a quick glimpse of a few years worth of data from 2000, 2002, 2004, 2007, I believe, a few different epochs to be able to understand how this object is changing. When you have exceptionally good data and some innovative thinkers, you can also go beyond 2D images, even 2D images over time. And what we're looking at now is the first 3D model of a supernova remnant using actual observational data from NASA. So we worked with a very talented scientist who was at MIT at the time, Tracy Delaney, to be able to take this data of Cassiopeia A, again, a lot of high energy data from Chandra, but also including infrared data from the Spitzer Space Telescope and optical data from some ground-based observatories to be able to place it into a 3D space so that you can understand which of the information is moving away from you and which of it is moving towards you. And by using some software that another very innovative thinker came up with, Dr. Alyssa Goodman and her team, that had been adopted from some local imaging folks at some hospitals that did brain imaging, we were able to come up with this very first 3D map of an exploded star. And when you consider objects in 3 dimensions, you can learn from them. In this case, the scientists learned that during this supernova event, it came apart in essentially 2 pieces, that spherical shell, and then also those opposing jets. And there's a lot, I think, to be learned when you start to consider all the dimensions of your data, whether it's over time or whether it's over space. So we took that same 3D model and just brought it into some Hollywood type processing 3D software to be able to map the previous data set into something that looked a little bit more spacey. And you're looking here at, again, this exploded star 11,000 light years away, and you're able to see around it, through it, above it, and below it, and get a very different sense of what this object is like versus if you're limited to only looking at it in 2 dimensions. And I just think that's quite lovely. So other things that we can do is when you have a 3D model, we can take it and make a 3D print of it. And this was something that we just started out for fun. We were very curious as to see how we could utilize 3D printing as another way of knowing and also as a way of communicating. And this project ended up turning into a whole new area of work for us. And we now do quite a lot of 3D models, 3D prints of our objects, because it's a fantastic way to be able to communicate with people, particularly for people who are either blind or low vision. Having access to the data in a tactile format just provides a very helpful way of knowing and making meaning. And we've done many different kinds of 3D prints now. We're still looking at the 3D print of Cassiopeia. This one is in color, and there are textures applied to their color, so you can actually feel the difference between where, for example, the iron is situated, which is out along the perimeter. You're seeing it here in green, versus where the argon or the silicon or the other material is dispersed throughout the remnant. So what started as a very fun project has led us to a complete program now in 3D modeling and 3D printing specifically. And that was just an incredible project to work on. We improved the models by working with students at the National Federation of the Blind, and they greatly assisted us in being able to make them all better. So we, for example, learned to cut models like Cassiopeia in half so that you could access the internal material. We started working with jets that we could attach by magnets so things could be taken apart and put back together. We worked on the detail of the pieces. We worked on the size of them, and the feedback was just definitely a highlight of my career. So we also had started to experiment with virtual reality, and as another way of kind of being able to represent and visualize this information. And this video is just one of my students. She's where it's in a lab at Brown University, and she is essentially getting to walk inside the supernova remnant Cassiopeia A. And the camera person is outside, which is why it looks like she's not inside, but she is actually inside, and she's learning again where the iron is. And the iron is along the perimeter, as I mentioned, I think in my last slide. And what's interesting about that with something like Cassiopeia A, we can study these exploded stars, and it's a great way to understand more about the star itself and how it lived. So it's kind of like reverse engineering, or like figuring out something through like a CSI crime scene. And it's this whole idea that, when a star like Cassiopeia A is aging and it's starting to run out of fuel, at its core, iron is building up. And so right before the explosion, when it's really happy, that iron is innermost at its core. And then in the explosion, as you can see here, as represented in this 3D model, that iron, which is shown in green, is now along the perimeter. So how did the iron, which was at the very centralmost region, become scattered along the perimeter, more or less? And part of the reason is that that star, Cassini A, when it exploded, it turned itself inside out. So this is a really wonderful way to be able to represent a star that not only exploded, but turned itself inside out, and help represent where all of that information, where all the calcium, the silicon, the sulfur, the argon, the neon has essentially scattered throughout the remnant, and to be able to map it, not just in 2D, which is also very helpful, but in 3D as well. And so this is just me in there, which is fun. I think anytime you can spend some time inside a virtual reality lab, you should take the opportunity. It is a very cool thing to do. We've also been able to bring it into augmented reality. So essentially cast this object in your office or anywhere else. So this has been a really fun project. I think if we watch this video for another 30 seconds or so, you'll see that they're actually going to build the remnant bit by turning on some of the various layers. So the silicon goes off, the iron goes off, then the jets, the high energy emission, etc. And then you can build your supernova right back up. So we can do other things as well. We can also bring them into holograms and do other types of digital representation. It's just a really fun area of study to be able to see where you can take this data and the different ways you can represent it. But starting last year with the pandemic, some of the methods of working with this data had to change because our labs were shut down, for example. Students had to go home and we weren't able to do the same things that we had been doing. We weren't able to meet and reach the same groups that we had been working with. Public groups, for example, groups of students who are blind or visually impaired, or groups of children at Fenway Park, what have you. There was such a huge stop, right, when the pandemic happened and everything just had to sort of pause. So we used that time as an opportunity to try and think a little bit out of the box and figure out what could we do to keep visualizing or representing this information in a way that would be useful, perhaps to researchers, perhaps to non-experts, and make it a valuable experience still. And we had some friends who had been working in data sonification, or essentially taking information and translating it into sound. And working with them, Matt Russo and Andrew Santaguida, we created a whole new program around this idea of data sonification. So I'm going to play for you, and hopefully you can hear what this information of Cassiopeia A, again, the supernova remnant 11,000 light years away, taking the intensity information that we're looking at on the screen right now and translating that into sound. So each different sound that you're hearing is a synthesized sound that has essentially been coded to those different chemical elements that I was talking about before, the iron, the silicon, the sulfur, etc. And so there's a sort of a chord that's forming, a mini little symphony that's being expressed from the different types of information that are available in this really beautiful representation of an exploded star. And by moving all of that information out at different angles, you're actually sort of able to hear or understand at some level about the expansion of this object and that it's changing. So let's go to the next slide. Okay, so I gave a very brief overview of what sonification was when I showed the example of Cassiopeia A, but essentially sonification is just this idea of translating information into sound and using audio, non-speech, so not just talking, to either represent or help perceptualize your information. This is an absolutely growing area in astronomy, not only for communications, but also for research and discovery. There are a number of projects and applications at a bunch of different observatories and other satellite centers that are being researched now as we speak. And there are a number of leaders in this field as well. Dr. Wanda Diaz is a fantastic leader in this field, and there are many others here listed as well. But it's just an area that has been really exciting, and another way to be able to take all of those ones and zeros, all of that information that was recorded, that is, in the case of the Chandra Observatory, inherently invisible, right? We can never natively see this type of information with human eyes because human eyes weren't built to be able to see X-rays or gamma rays or infrared light or what have you. So being able to translate the information from one form to another and not just focus on the sense of sight has been a really fun project to work on. I'm going to show a couple more examples of the different types of projects that we've been able to do and the different formats that might take. We've sort of established now a pipeline to help us take information from a 2D image into a 3D model. And then once we have the 3D model, we can 3D print it. We can bring it into virtual reality. We can kind of take it through all those platforms that I showed with Cassiopeia A. And we have a system now for being able to do that. Again, it takes really good data. With Cassiopeia A, the example I was showing before, our very good friend, we have over 2 million seconds worth of data. So it's a very rich, very deep clump of data that we can go back to many times. But there are many other objects as well where we have fantastic data on, and the data continues to grow as the mission matures and continues. So the Crab Nebula is another just lovely object to be able to look at. This is another bit of a remnant left over from an exploded star. And here you're looking at the leftover, very dense core, the pulsar at the center of that explosion. And you can see on the left is a 2-dimensional image, that's all X-rays. And on the right is the 3D print of the 3D representation of what that ring and jet structure looks like, and hidden at the intersection of the two jets would be the location of the pulsar. And this is what the crab's sonification sounds like. So these sounds that are synthesized sound a little bit more instrumental, more like a plucky violin for the optical data, and the infrared data as a lower synthesized note, and then the highest energy, the X-ray data, as like that highest note. So you can really hear the crescendo as you're approaching those high energy particles around the jets and the disk, and particularly as you're going right over the center. Where the pulsar is. So it's another way to be able to represent the information. And the next example that I'd like to show is another supernova, Supernova 1987A. Here we're actually looking at a simulation in the video at the top. That simulation has been constrained or tightened up, so to speak, by the actual X-ray observations from Chandra. So Supernova 1987A is a supernova that we witnessed here on Earth in 1987 and has been a very, very popular object of study ever since. Again, it's sort of like being able to see something happening in real time. I say real time, of course, but you have to consider that this is look back time. This is many, many thousands of light years away. So we are looking at the data much later, but being able to see it so clearly from Earth and see it changing over time has been really helpful. And many observatories have looked at it since the first ones that detected it back in 1987. And Chandra is one of them, Hubble, of course, as well, and radio observatories for sure. So there's a lot of great data, and being able to, again, simulate it into a 3D model that's been tightened up by those actual X-ray observations shows that what in the two-dimensional image from Chandra kind of just looks like a donut or ring is actually a pretty complex structure when you look at it from the side. So that 3D information just offers a very different way of knowing and understanding. And we were able to 3D print this as well. And then using a technique of like a radial sonification, where you are going around the rim and sort of going clockwise around the object. This is what that information changing over time sounds like. So I really like this piece for a couple reasons. Let me just bring it back up on my screen so I can talk about it, and I'll just pause. So this is a really lovely example of a data set to sonify, because you have this bright ring, and that ring is brightening even more so over time. And as the information that's being sonified, as you're seeing or hearing the position as it sweeps around that ring, you're essentially hearing all of those bright, fiery little knots that have been lit up by the X-rays sweeping out from that initial explosion. And so you can hear each of those little individual knots quite distinctly as you're sweeping around, as it's changing over time. So there's a lot of information to consider in this one sonification, or this one visualization, or this one representation. And each little piece of information just gives you, I think, a better sense of what sort of makes this object tick. And another reason I like this object so much is that the sound piece for this, that glass bowl, lovely sound that you hear, was actually recorded from a colleague of ours, Christine Malik, who is an amateur astronomer and who is blind. And her music was then used to create this data sonification. Just seemed very poetic and lovely. And Christine recently sort of described these sonifications in a beautiful way, saying that it's for someone like me who has sight and who spends all their time doing the visualizations, the sonification is a really wonderful form of dessert. And there is for sure stuff that you can learn from them. But for her, it's a meal in and of itself. And I really appreciated that description. I hope she doesn't mind that I shared that with you all. So this one is a newer object that we've sonified, and is just, I think, has so much potential for learning, because I don't think I've really talked about it yet, but this idea of using sound to not just represent information, but to be able to learn from it is just a huge area of interest and study. All of these other groups that are doing these projects are not just sonifying, for fun. It really is about being able to take data and not only make it accessible, but also to be able to analyze it and learn from it in different ways, because the human sense of hearing is really rather good. And so the idea that you can learn different things by listening to your data versus just looking at your data is a really valuable and enticing area to be able to study. But it also for sure helps astrophysicists and other astronomers and other scientists who are either blind or low vision to be able to access the information as well. So there's just, I think, a whole lot of deliciousness in here to be able to figure out. The next example I want to play for you is a stellar nursery. This is a very famous image made famous from the Hubble Space Telescope many, many years ago after they had launched and gotten their contact lenses on. The Hubble Space Telescope's first image of the pillars of creation, which was, I believe, 1995, was just iconic. And this is the updated observation from Chandra with X-ray data overlaid. So the X-ray data is like some of those compact sources that you're seeing dispersed across the image. And you're going to hear different sounds for that more nebulous, lower energy material from Hubble versus the sort of higher pitched sounds, slightly pluckier sounds for those individualized compact sources. So that's what you want to listen to as we're sweeping across the stellar nursery. One of the things that we really wanted to make sure was audible in this experience was this idea that these pillars of gas and dust are really tall. I think the one on the left is about 4 light years tall, so 4 times 10 trillion kilometers. And then the two on the lower right, so those are separated, all 3 are separated in space. And so let's see if you can pick up any of that as we listen to the translation of the data. So you can hear again these 3 different synthesized sounds. There's sort of that low droning synthesized sound of the sort of diffuse emission that's throughout the object. And there are those high pitched sort of plucky kind of sounds to denote the high energy astrophysics data. And then there's that sort of, I don't know, I kind of think of it as like a warbling drone as you're going across the very diffuse dust and gas that are forming those giant pillars, the giant pillars of gas and dust that are just really quite lovely. So that is another favorite. They're pretty much all favorites at this point, but however, I did want to zoom into the very center of our Milky Way galaxy for this next piece. This one is, dare I say, a favorite. I feel like I'm sounding like a broken record. But essentially, we've got 3 different layers of data here. We've got the highest energy material from the Chandra X-ray Observatory. We have the middle range material from the Hubble Space Telescope that is like a near optical infrared. And then we have the farther out infrared data from the Spitzer Space Telescope. And each one is assigned a different color. So if you're following along with the visuals, the blue is going to represent the high energy data, the yellow is representing the Hubble data, and the red is representing the Spitzer data. So in this case, again, these are all sonifications that we've been working on with our colleagues, Matt Russo and Andrew Santaguida. And in this case, we have assigned a sort of musical instrument type of sound, where the lowest energy material is a soft piano, and the higher or middle ranged energies from Hubble are like a violin, and that absolute highest energy, the X-ray information from Chandra, is a xylophone. And so this piece speaks to me in a different way, more musically. I was a total band and chorus geek as a kid. I'm a huge fan of like Eric Whitacre and other types of choral music. I love different music, some of the sort of experimental stuff that Imogen Heap works on. So this piece sort of spoke to that sort of auditory aesthetic, if you will. So as you're listening, we are going to be sweeping across the innermost 400 light years of the central region of our Milky Way galaxy. And you're going to be hearing, again, lots of different objects. You'll hear a very high-pitched object about a third of the way through that's a really bright cluster of stars. You're going to hear other smaller high energy little explosions around neutron stars and other types of events. And then as we get to the lower right of the image, you're going to hear a crescendo. And that crescendo is essentially letting you know that we are approaching the supermassive black hole itself, Sagittarius A star. It's buried deep in the brightest white spot of the image if you're looking at it. And if you're listening to it, you're going to hear it as a really loud, cacophonous type of production around that area. And then the sounds will drop off again as we finish the sweep of our data. So let me press play. So what I liked about this piece, and each of these sonifications, by the way, is available as an individual component so that you can play solos if you'd like of just the highest energy data or just the mid-range and just low energy, or you can play them together as a sort of mini symphony, which I've done here. But when you listen to each of them individually, you really can hear what different sounds, that cooler gas and dust in the infrared as you're sweeping across versus the many stars and sort of crispier filamentary structure that you'll see or hear in the Hubble data versus the very bright and energetic regions that come across via the xylophone sound for the Chandra information. And I think what I particularly like about it is when you get to that crescendo, it's like, it's the downtown area of our Milky Way, right? There's all this hustle and bustle about around that central region just outside the Sagittarius A star, supermassive black hole. And it really comes across beautifully, I think, when they're all three of them being played together around that area of very exciting, high energy, busy downtown, if you will. And so it is, I think, quite useful to think of this data when you're viewing it versus listening to it versus touching it, for example. It really does bring different perspectives and different information, I think, to your experience. So I have looked at this data specifically of the galactic center for almost 20 years. I've been very familiar with the galactic center. It was an early target of Chandra's, and the very first composite of multi-wavelength data from Chandra, Hubble, and Spitzer we created for it back in 2009. And so I felt so familiar with this data. And yet the first time I listened to it, this is the very first sonification from our new program with Matt and Andrew. And the very first time I listened to it, it was just like getting to experience this data that I thought I knew so well all over again. It was totally new. And I just caught different things that I had not paid attention to visually by just hearing those things. You can hear how well the infrared sort of hugs the optical, and you can hear it as you're sweeping across, like how well the X-ray brightness sort of fills in some of the voids of the infrared and near optical information from Hubble, for example. So again, just a really unique way of being able to not only experience the information, but to also be able to learn from it. So my next example is another new example. I can't seem to quite figure out the knack of going from a slide that has music on it without playing the sound again. I'll have to figure that out. But in the meantime, this most recent version that I will play for you in a second is the bullet cluster. And this is a cluster of galaxies that was pretty important for Chandra scientifically. It was an important result back in 2006 because this was the first direct proof, if you will, of dark matter. So most of the universe is actually dark. Like 95% of our universe is dark matter or dark energy, and just about 5% of our universe is stuff like us. So the stuff that makes up the stars, the planets, the few bits of people that might exist, and of course things like galaxies and beyond. And the rest of it is dark, and it's certainly going to be a challenge to study something that has no light output, that has no way of being seen directly. Instead, with this image of the bullet cluster, you're seeing the normal or baryonic material via Chandra and other telescopes. The Chandra part is in pink, and the sort of sprinkling across of the various galaxies is from Hubble, and that is in mostly like whites and yellows. And then the lensing map that shows the location of the dark matter is also from Hubble and ground-based observatories, and that's showing essentially the effect. So you're able to see the effect between the normal matter and the dark matter. So for this one, we again wanted to experiment with sounds that would really help demonstrate the difference between the dark matter and the normal matter, while still also being able to provide audio clues for the location or the sprinkling of the galaxies throughout this sort of plate. So that's what you're going to hear as we sweep across, and hopefully my sound, this one, the sound needs to be up a little bit because it's a lower sound, which can be a little harder to hear. But go ahead and put your sound up a touch, and I will press play and stop talking. So again, those plucky sort of sounds that you're hearing, they sound a bit violin-like, if you will. That is the optical information of all of the various galaxies and other compact sources. And then as you're getting close to the dark matter, you start to hear that low, slow sort of drone sound. And then as you're approaching the higher energy normal matter that's been wrenched apart from it, now you're hearing it as sort of like a higher pitched noise sound to be able to differentiate between the dark matter and the normal matter that's been wrenched away. So, I keep doing that. Next slide. So some of our early results from this data sonification project have been unexpected. We started off, my goal was to be able to help reach people that I hadn't been able to reach during the pandemic, but I did not expect to succeed in that goal beyond what I had been imagining. It went viral. Our first release was done in September, I think, last year. And within about a week and a half, we had over 1 million we're at like 1.5 million listens on NASA's SoundCloud. And that just sort of blew my mind. There was just a lot of significant news coverage, again, that I had not expected, and was just most pleasant to be able to experience. And it was the most popular feature on the Chandra website for 2020. So the most visited thing. Unexpectedly, that just kept going. However, we did a second batch of releases later in the year, and in the, I guess, 7 or 8 months since we started working on this, the sonifications remain in the top 50 of the thousands and thousands of web pages that Chandra has. People just keep coming back to them, and they are heavily played and downloaded, and it's been just really wonderful to be able to experience that. Very, very positive overall. The informational bits and pieces that we've been getting from people, sort of anecdotal responses and our own observations, have been that people talk about a very emotional response to this, and also things that it's curious, it's fascinating, it's beautiful, it reminds me of this music or that music, and I didn't know you could listen to these things, I didn't know you could translate information this way, and it's been really exciting, I think, to witness that. And as a way to help us quantify this, one of the things that we just released last week is a new study. So please do point your browsers this way if you have any interest at all in the last, I guess, 40 or so minutes that I've been speaking. We are very much looking forward to improving the way that we do these sonifications and learning what you're learning from them. So this is a new study that we just launched to help us understand that all. If you go to surveymonkey.com/r/Chandra Sonify, you can participate in our study. It's for experts and non-experts. It's for sighted and blind or visually impaired people. We would really like to get as much data as possible and truly get your input to improve these, but also understand what everybody else is understanding from these. So, and again, we've had fantastic response so far, but I am very greedy and would like yet even more data. So if you have the time, people have been telling us that it's the most fun survey they've ever taken. And I have to be thrilled that because I don't know if I've ever called a survey fun before. So I was really, really happy to have that result. So please do feel free to participate. Anyways, these are the types of things that I like to think about. These are the types of things that I like to show and play. And yeah, if you're interested in learning more, just check out our website too at chandra.si.edu. Many thanks to all the partners. We do not work alone in any of these projects, and I am very fortunate to have a very talented and wonderful crew around me, whether geographically or not. And I list just a couple of people that have helped specifically to the data sonification, but there are so many more people that have been involved in that really should be thanked. Also, if you're attending South by Southwest 2021, I have a panel there about the same topic where you can learn a little bit more about it from some of the experts I've been able to work with. Please feel free to check that out. And I know the videos will be going public. If you're not attending South by Southwest, they will be going public afterwards for free for everybody as well. So you can search that later on. But everything that we've presented here today is essentially public domain. So if you're interested in learning more, if you go to chandra.si.edu/sound, you can access the sonifications. If you go to chandra.si.edu/tactile, you can access some of the 3D prints that I've talked about. If you go to chandra.si.edu/VR, you can access the virtual reality applications, and more is coming. So yeah, thanks. I hope you all enjoyed it.
Thanks, Kim, for sharing everything that you're working on at this time. I think it's a very interesting and fascinating work that you're doing. It's such a great way to look at the universe, and especially like we can look at it like we're right there out there in the universe ourselves. And the sonification is a way I see as combining science and art together, and It's really different than a great sound that I'm hearing there. So thank you very much for your presentation.
Thank you. Thanks. I hope everybody enjoyed it.
As far as we do have a question here, is how do you choose the direction at which to sonify an image?
So that is a very good question and very relevant to any way that we would represent our information, for example. So whenever we're working on a visualization or representation in some way, essentially we have to make choices. As mentioned from the talk earlier, none of these are space selfies or space recordings of the sound or the visual. They are all translations of information from one form into another. So this observation is captured and then you have to do something with that data. So in the case of the images, we do definitely have sort of loose guide, I guess you would say, to how we typically approach that. But it's always driven by the science. And I think specifically going to the data sonifications, it's very similar. Each data set has a story that we are trying to communicate or present in the best way possible to stay true to the science while still making the experience informative, enjoyable, what have you. And so for each of those cases, whether it's a visual or sound, you of course are human and you're bringing your own perspectives or your own biases, if you will, to the information and what the resulting output is. But you're letting that science drive you throughout the whole process. And it has been our experience so far that these data sets sort of tell us, that might sound weird, but I think you probably know what I mean. These data sets kind of direct where we need to go. And it might take some experimenting to figure out which sound or which color, depending on what you're doing, best fits the science and best fits the data. But it is sort of something that kind of shows you if you listen to it, I guess pun intended. So for example, with the idea of the galactic center, which was the very first one, that data is pretty distinct. The way the Hubble data versus the Spitzer data versus the Chandra data are all laid out in that long image. It's very easy to see kind of like where all of the features are, and that sort of distinction that each different type of material is showing you translated really well to that symphony type of sound by being able to apply the piano, the violin, and the xylophone. Each of those three sounds is distinct, but they also blend well together. And that was kind of the point. We wanted to make sure that each solo made sense, but that then together as one piece, it would be cohesive, both as an experience and also hopefully as something to enjoy. So for other sounds as well, when we started working on Cassiopeia A, for example, that one was actually pretty tricky because that is a spherical object and not just a simple flat left to right pan. That data had to be approached differently. And because there's so much informational and sciencey goodness crammed into that image or to that data set, we definitely had to think strategically about how to be able to pluck out some of those individual notes, if you will, those individual chemical components, while still providing a sense of the whole unit, that this is a remnant that is expanding over time. And I really have to give so much thanks to Matt and Andrew, who had been doing data sonification for years before I dipped a toe in the water, and their expertise has just been invaluable for guiding this project in a way that not only was able to portray high energy astrophysics data, which is where I'm coming from, a place of, centering on the Chandra data, but then also being able to take in consideration the other multi-wavelength bits and pieces of those objects. So yes, I hope that answers your question. It's a good one.
Okay, thank you very much. I don't see any more questions.
Great, I guess I did a good job then.
Several comments there that we had one comment that said, how do you, or the survey is awesome and definitely worth your time. So sounds like everybody ought to go on and complete the survey.
That's great. Thanks. That is great. Thumbs up for whoever said that. I really do appreciate people's time taking the survey because it is a user study. It helps us improve what we do. And if we don't know how people are perceiving this data, we can't fix it and make it better. So yes, please do fill out the survey. It's not painful.
Okay, another comment, just great talk and wonderful images, and I think we can all go along with that. So
great.
Thank you a lot, and good luck on bringing us more of this to us.
Thank you. Thanks. That was easy.
And thanks to everyone who attended today. Our next presentation in this series will be in 2 weeks, March 17th at 10 a.m. Mountain Standard Time. Now for most of the country, this will be an hour later than what you're looking at it today because you'll go on daylight savings time, but we here in Arizona don't go on daylight savings time. So we're going to be at 10, but you're going to be an hour later. Our speaker at that time will be Dr. Winston Benbow. He's the director of the Very Energetic Radiation Imaging Telescope Array System, otherwise known as Veritas, and he'll be speaking about current gamma ray research and the future of gamma ray science. And for those who live in the area of the Whipple Observatory, you might be familiar with the large mirrored dishes that can be seen at the visitor center, and that is Veritas. So it's a great opportunity to find out more about the work that's going on right in your backyard. Future topics include South Pole astronomy, Parker Solar Probe, Betelgeuse and the Sneeze. That sounds real interesting. And black holes. So we've got a great lineup coming. So keep joining us for all of these great speakers. And you can check on the Fred Lawrence Whipple Observatory website and get a schedule on what days all of this will be and make plans for it. And with that, we're going to end our presentation, and thanks for everybody coming.
Thanks.